an is equal to 2 plus 2n squared. What can you say about the sequence? When n is very big, what do you expect?
A bigger number.
Big, as big as you like. And then once again, you can set a standard of being big. The million is big enough, then I can find you a capital N to meet your challenge, such that once you get past the capital N term, all the subsequent terms will be big enough based on your standard. Right, every single term. All right, and so we have this concept. This next one. Let's A1, A2, be a sequence. Okay, we say limit n go to infinity, an is equal to infinity. You dealt with that before, right? With the case of function, right? Back in calculus 1. You say that the limit of this function that x approaches 1 is infinity. Right? And or when x goes to infinity, this function approaches infinity. Right? So what does that mean? If for every challenge, for every epsilon greater, for every m, for every big number, the epsilon, by the way, I didn't mention that, but epsilon is a Greek letter. That is a Greek counterpart of E. And E usually stands for error. And error is not necessarily mistake. Error is more like error tolerance, tolerance. And so we refer to small tolerance, we usually use epsilon. But here we're not talking about small number, right? So I shouldn't use epsilon. So for every, let's say, capital M, which is greater than 0, which is meant to be big, okay, there is a natural number, capital N, to meet the challenge, i.e. such that for all little n greater than capital N, we have an is greater than that m that you set. For example, if you give me not 1 millionth, but rather 1 million, big number, right, 10 to the 6th power, right, big number, give me, then I can assure you that I can find, some term, so that once you get past that term, all the subsequent terms, every single one of them, will be that big, bigger than a million. I guarantee you. If you can guarantee that, then we say that this sequence converges to infinity. And so here's the remark. If n goes to infinity, an is infinity, then technically, then an is converging or divergent. It's actually divergent. Because convergent means convergent to some L, some number, like 3. It doesn't allow for, infinity. All right? So when you are sure that limit is quote-unquote infinity, then that essentially the limit doesn't exist. Technically, the limit doesn't exist. Technically, the sequence diverges, except that it diverges in a certain manner. If it diverges, doesn't have to diverge this way. It could go, it could oscillate like crazy, right? Okay, and so an is divergent, except that it diverges in a particular way. Okay, but technically you should say that it is divergent, except that it diverges in a certain way. And likewise, erase this part. Likewise, if I have limit n goes to infinity, a n is equal to negative infinity, that is what? That is also similar. Okay, so you give me it's very negative. So how negative is called negative? Give me a negative m. M is a big number, like a million. Negative m, very negative number. And then I assure you that I can find the n such that once you get past the n term, all the subsequent terms will be that negative, every single one. And if you can guarantee that, no matter what stringent the challenge, and no matter how negative the challenge is given to you, then we say that this sequence has, it converges, it diverges to. Probably it's better to say it diverges to negative infinity. Probably it's not appropriate to say that it converges to negative infinity. Likewise here, I probably should say that it diverges to infinity. And if I have, say, a n, here's a simple example. A n is equal to negative e to the 2n. Then what can you say about this one? Does a n converges? No, it diverges. But it diverges in a nice way. It diverges to what? Make sense? Yeah, because this can be as big as possible, right? Negative, but as negative as possible. Once we get past a certain point. All right. Next example. A n is equal to negative 1 raised to the nth power times n squared.
N squared or m squared?
N squared. N squared. What can you say about this one? First of all, it diverges. Would you agree? It doesn't stabilize to anything. And nor can you say that it diverges to infinity, can you? Because it keeps oscillating. Likewise, it doesn't diverge to negative infinity. So it's nasty. All right. Okay. So this one, limits n approaching infinity, a n is not equal to infinity. Likewise, this one you cannot say that it is equal to negative infinity, right? And in fact, and you cannot say it converges either. So it's nothing. And likewise, next example, a n is equal to negative 1. Okay. Raised to nth power. What can you say? You start with negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1. What can you say? Technically. Limit n goes to infinity, a n doesn't exist. And likewise, the previous example, limit n goes to infinity, a n doesn't exist. Except that sometimes this kind of description is kind of ambiguous. Like this one, it actually doesn't exist, but we still say that it's equal to infinity. I just say that it doesn't exist, it diverges, but it diverges in a certain way. Okay. All right. So now I'm going to very quickly list a sequence of, a group of rules, limit rules, which is very similar to the limit rules that you are familiar with from Calculus 1. And I'm not going to prove them. Each one of them can be general rules. They are not particular to a particular sequence, like a n is equal to 1 over 1 plus n. It's not like that. It also, all these rules refer to, as we recall, general situations. And therefore, if you want to prove them, you have to prove it in a general manner. But it's not so hard to achieve. Okay, so you use those, previously you used epsilon delta proof, and then now you use epsilon n proof. It's very similar. And so you can prove the following.